Welcome to the deep dive. We love plunging into fascinating topics, and today we're definitely tackling one of history's great cosmic mysteries, the Tunguska event. Just try to picture this. It's June 30th, 1908. You're in central Siberia, deep in this remote taiga forest. And then suddenly, out of a clear sky, bam! A colossal explosion. It flattened millions and millions of trees over an area bigger than many major cities. But here's the kicker. No crater. Nothing. It's this enigma it's kept scientists guessing for more than 100 years, and we're going to try and piece it together for you today.
Absolutely. And the scale, the scale is just staggering. We're talking about one of the largest impact events we know of in recent centuries, the energy release, estimated around 10 to 20 megatons of TNT.
Wow.
Yeah, which is, way more powerful than the bomb dropped on Hiroshima. But like you said, the crucial point is that it seems to have been an airburst. It exploded before hitting the ground.
Right. And that's our mission for this deep dive, really. We've got these archival histories, NASA research, risk analyses, a whole stack of material. We want to pull out the most important insights, follow the scientific journey, understand the history, and maybe even explore some of those what-if scenarios that pop up. It's this mix of science, history, and, a bit of cosmic head-scratching. Okay, so let's dive in. That morning, June 30th, 1908, it must have been terrifying. The eyewitness accounts, some were collected much later, but they talk about this bluish light, bright as the sun, just streaking across the sky, and then a fire pillar that apparently split apart, followed by a sound. People described it like artillery fire or this terrible thunder, even though the sky was clear.
Exactly. And the effects weren't just local. People were reportedly knocked off their feet over 100 kilometers away.
100 kilometers?
Yeah. And windows shattered hundreds of kilometers further out. It must have felt, like you said, apocalyptic for those nearby. And the physical effects registered much, much farther away.
Right.
We saw seismic waves across Eurasia, basically equivalent to a magnitude 5.0 earthquake on the Richter scale.
Right.
And that's not all. The atmospheric pressure waves, the shock waves in the air, they actually circled the entire globe. Twice.
Twice. That's incredible.
It is. And then there was that really strange phenomenon of the light nights.
Yes. Tell us about that.
For several nights afterwards, across northern Europe, the sky had this unusual glow. People could apparently read newspapers outside at midnight without any artificial light.
Weird.
The theory is that it was caused by fine ice particles thrown way up into the high atmosphere by the explosion, scattering sunlight.
Okay, so you've got flattened forests, global shock waves, weird glowing nights. But, as we said, no impact crater. That seems like the central puzzle, doesn't it? After something that big, you'd expect a hole in the ground.
You absolutely would. And that's what baffled the early expeditions. The most famous one was led by Leonid Kulik, a Russian mineralogist, in 1927. He finally reached the remote site, expecting to find meteorite fragments, maybe a huge crater.
And found?
Well, he found a devastation, all right? This vast area, over 2,000 square kilometers, that's something like 80 million trees, just flattened. And they were laid out in this distinct radial pattern, almost like a giant butterfly shape fanning out from a center point.
The butterfly pattern.
Yeah. But right at that center point, the epicenter, no crater. Instead, the trees there were scorched, kind of like telegraph poles, still standing upright, but with all their branches stripped clean off.
Just standing there, scorched.
Exactly. And this total lack of a crater combined with the sheer scale of the destruction. Well, it really fueled speculation. For decades.
It did.
It became, prime fodder for science fiction, especially in the Soviet Union. There were theories about nuclear power alien spaceships having accidents, all sorts of things. Siberia sort of became the original Area 51 for a while there.
Okay, so fast forward. The mystery lingers, but science doesn't stand still. We get better tools, better models. And then more recently, the Chelyabinsk meteor event in 2013, that smaller airburst over Russia, that kind of reignited interest, didn't it?
It absolutely did. Chelyabinsk provided invaluable modern data on what an airburst looks like and how it behaves. It really spurred a new wave of research into Tunguska. There was a key workshop at NASA Ames in 2018, bringing together international experts. They applied modern computational power, sophisticated simulations to really re-examine all the evidence.
And what's the picture that emerged from all that modern number crunching?
The scientific consensus now is pretty strong. Tunguska was almost certainly caused by the airburst explosion of a stony asteroid.
Okay, and an asteroid. How big are we talking?
The estimates are somewhere in the range of 50 to 80 meters in diameter, so, pretty big but not mountain-sized. And it seems it detonated at an altitude of about 10 to 14 kilometers above the ground.
10 to 14 kilometers up.
Right. and releasing that huge amount of energy, 10 to 20 megatons. These advanced computer models called hydrocode simulations were really key. They let scientists simulate the asteroid's entry, its breakup, the explosion, even factoring in things like the terrain and the forest properties below to refine those estimates.
That paints a much clearer picture. An asteroid 50-80 meters across, exploding high up. But why? Why an airburst? We tend to think of space rocks hitting the ground, right, making craters. How does something that big just detonate in the atmosphere?
It really comes down to the physics of atmospheric entry at incredibly high speeds. As this asteroid slammed into the Earth's atmosphere, it experienced enormous aerodynamic pressure and intense heat.
Like hitting a wall of air almost.
Sort of, yeah. An increasingly dense wall. The pressure builds up incredibly fast, and the heat generated by friction is immense. For a stony asteroid of this size, traveling at many kilometers per second, the atmospheric stresses eventually overwhelmed its structural integrity. It basically just disintegrated catastrophically. All that kinetic energy was converted into explosive energy, released very suddenly high up. That's the airburst.
So it blew itself apart before it could reach the surface.
Precisely. That's why there's no crater. And some research suggests that if the asteroid was porous, had internal voids or weaknesses, that could actually make it fragment even more easily. The atmosphere, in this sense, acts as a pretty effective shield against objects up to a certain size. Now, another really critical part of understanding Tunguska is looking at how its energy was distributed. Its environmental fingerprint, you could call it.
Okay, the fingerprint, what does that tell us?
It tells us it was very different from, say, a nuclear explosion. With nuclear bombs, a lot of energy goes into heat and radiation. But Tunguska, it seems around 99%, the vast majority of its energy went into the blast wave, the shock wave.
99% into the blast. Wow. And we see the effects of that power.
Oh, absolutely. The sources talk about deer being killed near the epicenter, purely by the pressure wave. Those shattered windows hundreds of kilometers away.
Right, you mentioned windows shattering 500 kilometers away, and people knocked unconscious for days.
Exactly. There are these measures of overpressure, the sudden increase in pressure from the blast, maybe 200 kilopascals, that can be fatal. Big buildings might collapse around 50 kilopascals. Glass breaks at just 2 to 7. Tunguska's blast wave clearly delivered devastating pressures over enormous distances.
Okay, so almost all blast, very little heat by comparison.
Exactly. The thermal radiation, the light energy, was estimated to be only about 1% of the total energy release. And we can see that limitation in the tree damage. Significant charring and burning seems confined to maybe 15 kilometers or so from the epicenter.
And you mentioned trees surviving quite close.
Yes, that's crucial. They found surviving trees, some even with live branches still attached, less than 7 kilometers from the epicenter. Now think about this. Just heating pine needles to 60 degrees Celsius for less than a minute is enough to kill them. The fact that trees survive so close really underscores how relatively weak the direct thermal pulse must have been compared to that overwhelming blast wave.
So this specific energy split, mostly blast, very little heat. Does that point towards a specific type of event?
It does. It actually supports this idea of maybe a volumetric explosion.
Volumetric, what does that mean?
Well, instead of a single point explosion, like, a bomb going off at one spot, imagine the energy being released over a larger volume of space almost simultaneously. Perhaps as the asteroid broke up, it created a dispersed cloud of fragments and superheated gas mixed with atmospheric air, and that whole volume detonated.
Okay, like a fuel air bomb or a giant dust explosion, maybe.
Something along those lines, yeah. A more diffuse explosion. And that kind of volumetric event would naturally channel more energy into the pressure wave, the blast, rather than concentrating it into intense heat radiating from a single point.
And that matches the Tunguska fingerprint.
It matches it very well. It really changed how scientists thought about these things. Tunguska showed us that cosmic impacts aren't just about craters. These atmospheric explosions can be incredibly destructive in their own right, even if the object doesn't survive to hit the ground.
Okay, so if this massive airburst happened in 1908, how often do things like this actually occur? What's the risk?
That's a really important question, and the estimates have actually changed quite a bit over time. For a while, people thought maybe Tunguska-sized events happened every few centuries, maybe 200, 300 years.
That sounds quite frequent.
It does. But more recent studies, including work discussed at that NASA workshop, drawing on better detection of smaller events and modeling, they suggest it's much rarer. For an impact over land, a Tunguska-scale event, 10-20 megatons, is now thought to occur maybe only once every 1,000 to 4,000 years.
1 to 4,000 years. That's a big difference.
It is. Much less frequent. But smaller events, like Chelyabinsk, that was about a 20-meter object, much less energy, those are estimated to happen roughly once a century, somewhere on Earth.
And the reason we haven't recorded more of these big Tunguska-like events in history, it's partly location, 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 right?
Exactly. About 70% of the Earth's surface is water. So statistically, most impacts are going to happen over the ocean, where they'd likely go unnoticed unless very close to shore or shipping lanes.
Right. An invisible splash.
Pretty much. And even over land, vast areas are sparsely populated or completely uninhabited, like Siberia, where Tunguska hit. So many impacts could have happened throughout history without leaving clear human records. One source called it an invisible hazard.
And we do know of others besides Tunguska and Chelyabinsk.
Oh, yes. There was the Sikote-Allen event, also in Siberia, in 1947, that one actually produced craters because it was an iron meteorite that survived entry better. And since we've had satellites monitoring, especially military satellites looking for nuclear tests, they've detected numerous airbursts over oceans and remote areas. Some quite significant, though maybe not quite Tunguska scale.
So these things are happening just often out of sight, out of mind.
That's right. Tunguska really woke us up to this more active cosmic environment, this sort of silent threat that we're still figuring out how to track properly.
Which brings us to the sobering part, the what-if scenario. What if Tunguska hadn't happened over remote Siberia?
Yeah, that's where the risk assessment comes in. Studies have modeled what a Tunguska-type airburst would do over a major modern city. One specific example used Manhattan, New York City.
Oh, wow. Okay.
The results are, well, they're catastrophic, frankly.
Yeah.
Property loss is estimated at around $1.19 trillion. Trillion, yes. And human cost, estimated 3.2 million fatalities and another 3.76 million injuries.
That's almost unimaginable.
It is. And the analysis also pointed out that the financial losses alone would likely overwhelm the entire global insurance and reinsurance market capacity. It's just off the scale of manageable disasters we typically plan for.
That really puts it in perspective, a chilling thought. But, despite this strong consensus about the asteroid airburst, are there still loose ends, lingering questions, or alternative ideas?
There are always a few, which is healthy in science. One ongoing point of discussion is Lake Checo.
Lake Checo?
Yeah, it's a small lake relatively near the Tunguska epicenter. Some Italian researchers proposed years ago that it might actually be the impact crater, or at least formed by a fragment.
Ah, so maybe a piece did hit the ground.
That's their argument, based on the lake's shape and sediment studies. However, other researchers, particularly Russian teams who've done extensive fieldwork there, strongly dispute this. They argue the lake likely predates the 1908 event based on tree growth rings around it and deeper sediment cores, so that's still debated.
Interesting. Any other alternative theories still kicking around?
Well, you occasionally hear mentions of older geophysical hypotheses, like a massive natural gas explosion from underground deposits, or even more exotic ideas, like a glancing impact, where maybe a very strong iron asteroid just skipped off the upper atmosphere and went back into space.
A space rock skipping stones off the Earth.
Kind of, yeah. Most evidence points strongly against the energy release pattern, the lack of specific geological markers for gas, the physics of a glancing blow. But they linger in some discussions, partly because the event was so strange initially.
It shows how science keeps probing, I guess. Even when there's a strong consensus, people keep testing the edges.
Exactly. It ensures the main theory is robust because it has to stand up to scrutiny and alternative explanations. The airburst model does that extremely well for Tunguska.
So what a journey we've taken. From this totally baffling mystery back in 1908, something that sounded like science fiction,
Right,
to this detailed, scientifically modeled cosmic airburst. We've seen its incredible power, that unique environmental fingerprint mostly blasts, little heat, and how our understanding of how often these things happen is still evolving.
It really is a remarkable story of scientific detective work spanning over a century. And I think the key takeaway, for me anyway, is how studying this event in remote Siberia over 100 years ago gives us absolutely crucial insights for today.
Yeah.
For planetary defense.
Yeah.
It highlights this very real, albeit rare, threat from cosmic impacts.
Yeah.
When you see those photos of the trees all pointing away from that empty center, it really drives home why understanding these events is so vital. It's this stark reminder that Earth is part of a dynamic cosmic system, constantly interacting with objects from space. And while these big events are infrequent, their potential consequences, Well, they're profound.
Absolutely. It makes you think, doesn't it, about the constant effort of observation, of modeling, trying to understand, and maybe even prepare for what might come from out there. It's a reminder that the quest for knowledge, especially about our place in the universe, it really never stops. There's always more to discover.